Hi, everybody. I'm finally back on the regular schedule. Christmas and the holidays otherwise are over, so back to business. All right, so last time, which was a while ago now, we were talking about we had done methods, and in the first little bit of closures, let's just kind of review what's going on here with closures. So this syntax was this vertical bar business, um, and okay, so closures are functions that can capture the enclosed environment. So the idea is that hey, we can use the variable from the surrounding context inside our method without having to pass it as a parameter, basically. And we didn't have to give them names, so they're anonymous methods or functions as well. So that's kind of handy. So we can capture the surrounding environment, and we don't have to give them names. And naming is a hard computer science problem. So, you know, that eliminates one of those things that we have to screw around with. Okay, so calling a closure exactly like calling a function. We have so there's a function and there's a closure and there's this vertical bars which kind of indicate, hey, we want to increment I by 1. And in this particular case, we didn't actually capture. There was no external stuff to capture, I guess. Here, closure annotated I, closure inferred I. So you call it like you call a function, but it can get to use other things besides the past parameters, I guess. And then there's something about inferred types. Okay, let's move on to factory review. Okay, closures are inherently flexible and will do what the functionality required to make the closure work without annotation. So then I remember doing this. We talked about, hey, it's going to figure out whether you want a reference or a mutable reference or just the value based on the context of how you use that thing that you're capturing. And it's going to take care of it. So they preferentially capture variables by reference and only go lower when required. So by reference, and then maybe mutable reference, maybe value. Okay, I assume that's what they meant by lower. So if I want to use color, print line only requires arguments by immutable reference, so it doesn't impose anything more restrictive. Yeah, so we just need the immutable color for print line, so we use it. And we can call print. And then there's this reborrow business. Color can be borrowed immutably again because the closure only holds an immutable reference to color, so sure. Whatever. Yeah, so there's this, again, we're kind of on the cusp of this borrowing thing, which has been mentioned over and over again without real explanation so far. But it seems to be related to, and I'm kind of guessing here that it's related to the whole memory management thing. So if we have possession of a variable, nobody else can have possession of that variable. And when I say we, it's not the global we, it's this particular line of code we. Right? So if I try to do something to modify a variable, but somebody else, some method or function or whatever has control of that variable, I'm not going to be allowed to make the modification until that thing releases it. Okay, so, and I guess there's an example here, this count plus equals 1. A closure to increment count would either take mutable count or count, but mutable count is less restrictive, so it takes that and immediately borrows count. The mut is required on ink because a mut is stored inside, right? So we need to say, hey, ink is mutable because we're doing a mutable thing inside. Thus calling the closure mutates the closure, which requires mut. Okay, and there's our inc. All right, and we kind of did this last time, right? Where we tried to reborrow, and then an attempt to reborrow will lead to an error, right? We kind of played around with that, where we can increment twice, but if we borrow count a second time, it won't let us do that because it's already been borrowed, because increment owns it, right? Because increment is the one that's going to be adding 1 to count. So if we try to borrow it for other purposes, it's going to say, no, you can't do that because there's this other thing that's going to happen here that's borrowing it. But once it's done, there's no more calls to increment, then we can borrow the count, because then the compiler is going, well, yeah, sure, we're done. Inc is done doing its work. So now you can go ahead and borrow it for a different context. And then we've got this box thing, which still haven't quite figured out the box thing. A non-copy type. Movable, box, new, 3. Mem drop requires T, so this must be taken as a value. A copy type would copy to the closure, leaving the original untouched. A non-copy must move. And so movable immediately moves into the closure. What are you saying to me? Mem.drop movable. Mem.drop requires a T. Okay, so we're, all right, fine. A copy type would copy into the closure, leaving the original untouched. A non-copy must move, and so movable immediately moves into closure. That sentence still doesn't make any sense to me. I think, let's see. A copy type would copy into the closure, leaving the original untouched. Okay, that makes sense to me. That sentence makes sense. So if we make a copy of something, the original is still in the original place. So if we talk about memory addresses or blocks of memory, so we have one block of memory with the original, and then if we're making a copy, obviously we have a second block of memory, and we take the values, the contents of the first block of memory, and write it into the second one. Okay, and so the original is untouched. If we modify the copy, the original, nothing happens to it. Okay, that much I understand. Now the next sentence, a non-copy must move. A non-copy what? A non-copy... Oh, a non-copy. Okay, so the non-copy must move? Oh, okay. So if it's not copyable, then the ownership must move. I think that's what they mean. Must move. The ownership must move. And so immediately moves into the closure. So movable immediately. What? Oh, the variable movable immediately moves into the closure. Okay, so the closure owns movable. Right. Okay. The closure, this closure here, owns movable at this point because it could not be copied. Okay, and it couldn't be copied because we're going to do this mem drop, which is going to say, yeah, we're releasing this memory. Okay. Consume consumes the variable, so this can only be called once. Consume. If I call it again. So what's consume? We scroll back in. I remember doing this. Where is consume? Where are you, consume? Oh, consume. Sorry. Consume is the closure that we just defined. So we dropped the movable, and then if we try to drop the movable again, we can't because it's already been dropped. You can't release memory twice. So you can only release memory once. Now this all makes sense, from a memory point of view. The syntax is a little interesting, but logically it makes sense. And I guess what they're trying to do is they're trying to make sure that you do not release memory twice, because that's actually something that can cause bugs as well. So in C, if you free something and then you call free again with the same memory pointer at some later point, you potentially, somebody else has used that memory space or parts of that memory space, or block of memory, and allocated them for some other purpose, and then you call free. And then, so what was going on under the covers back in the day when I was still working with C, which admittedly was a long time ago, the malloc was, it was implemented with a linked list, and the linked list had pointers to the next block, and so it had a, and so if you would hunt down the, and so memory would get fragmented after a certain point, because originally you would start off with one block of memory, and it would say this block of memory, all of it is free, and then you say I need some, so then you grab a chunk of it, and then you end up with two blocks, one on the used list, one on the free list, right? Whatever's left over is on the free list. The thing you needed was on the used list. But then, and then you could allocate like 3 or 4 blocks of memory. So now you have, whatever, three blocks of used memory and 1 block of freed memory. But then if you free that first one, now you have non-contiguous blocks of memory, right? You've got the first block, which you've just freed, and then 2 more used memory blocks kind of some length in the middle, and then you still got your really big block of free memory. So the algorithms were trying to do merges. They were looking at saying, okay, let me walk down the list of used memory and release it, and it would, because it was a linked list, you when you called free, you would just pass a pointer, and the pointer would, in some code back in, what was it? Sorry, Palm Pilot days, the Palm Pilot C compiler would assume that what the pointer you passed to it was a valid pointer. And so it would try to do its linked list manipulation right there. And that's a problem if you're not pointing at an actual block of memory, because that header and footer that contain the next and previous items of the linked list and the lengths and all that stuff are just random memory. So then, potentially all hell breaks loose, and you end up with this chain of links that point to nowhere. Anyway, so the point here is that this is trying to prevent that by saying, listen, this thing got released, so it got dropped, so you can't drop it a second time because it's already been dropped. And that makes perfect sense. Perfect sense to me. Okay, but the syntax, though, I guess it's because the compiler needs to figure this out. So we need to have some kind of, rules and ordering and stuff like that. But it makes it interesting because so far, all we've talked about is within a method, within a function. We haven't really gone, and so in the back of my mind, I'm thinking, how does this work across, like in a large system where you've got multiple methods and functions, and you need to pass memory around from place to place to place. And I suppose it kind of follows the same way, I would guess, is that if I pass it into you, the child function, then the child function is now the owner of it and can do whatever it wants to it. And if the child is the owner and the child frees it, then if I, as the parent, try to free it again, that the compiler is going to notice that I've done that, that's fascinating. The compiler is going to notice that. Now, I've written code like to do. We had so many bugs. I was working on this one system. We had so many bugs, memory allocation, that I wrote my own gated malloc with guard symbols and just made sure that the symbol existed and it wasn't going to free anything where the symbol, that the special symbols were not in the right places and blah, 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 blah. Because what ends up happening is with these memory errors is that, code over here is executing and freeing up memory and doing damage, and it's code over here that in some other place at some other time that actually feels the effects of it. And so tracking down where did the problem happen is actually quite difficult without some kind of headers, and the memory allocation code that we had back then did not have that, so I had to add it myself. Anyway, okay, so then let's see. Use move before vertical pipes forces Clojure to take ownership of captured variables. So move, needle, haystack. Oh, I see. So move, that's a keyword, move, needle, haystack, says you own contains, is going to take ownership of haystack, I guess. There are, in haystack, uncomment line above will result in compile time error because borrow checker doesn't allow reusing the variable after it has been moved. Removing move from the Clojure signature will cause Clojure to borrow haystack variable immutably, hence haystack is still available and uncommenting the line above will not cause an error. Okay, so my only question is, why? Oh, because this is contains. Okay, so we're calling the same function twice. So it's not like, I'm looking at this going, but I'm calling contains twice. So why doesn't the second contains fail? And I guess it's because contains is the owner. Not that particular instance of contains, but contains is the owner of haystack. Therefore, I can call contains as many times as I'd like, which actually kind of makes sense because ink here, right? Ink was called twice. Ink could have been called 17 times, and it still owns count. So it's not like an individual instance of ink is the owner. It's contains is the owner. Okay, and if I force, by using move, if I force contains to own this, then nobody else can own it, which means haystack.length. Now that's actually weird though, right? Because, okay, fine, haystack.length. Now why would I not be able to find out the length of haystack? Because that's not modifying haystack in any way. That's just saying, hey, haystack, how big are you? Which seems like it should be something that would be available to me whether this code owns haystack or not. But it does not allow that. So it's saying, no, haystack is owned by contains. You cannot look at haystack at all until it gets released. So how do you... All right, so if I've moved it, how do I unmove it? Are you gonna tell us how we're gonna unmove this? Because this is the thing I want to know. Is like, is there something I can write, some line of code I can write right here that will say, okay, I'm done with haystack. It doesn't need to be moved anymore. But it doesn't seem to be true because this says even after there's no more containses, right? So unlike here where ink, if we try to add some code in here and it said no, you can't do it, but once we got past all the inks, then we were able to reborrow and use it. But here, when we did the move, where it's done, it's gone. We can never ever use it again, which is really weird, I think. Like, why? I don't understand. The borrow checker doesn't allow reusing a variable after it has been moved. So move is different than owner. Well, so this muted this what? Well, in this case, we took a reference to the mutable, right? We took a mutable reference. So we had a mutable reference. In this case, we've moved it. So this is like a more stringent ownership, I guess. Okay, but we're not. It's like, all right. So let me just do this. Rust lang move versus not ownership, mutable reference. Okay. Ownership and moves. All the way down to 15. Huh. Because variables are in charge of freeing their own resources, resources can only have one owner. This also prevents resources from being freed more than once. Now, note that all variables own resources. Not all variables own resources. When doing assignments or passing functions by value, the ownership is transferred. In Rust speak, this is known as a move. Okay. So yeah, ownership is transferred. After moving resources, the previous owner can no longer be used. No. The previous owner can no longer be used. The previous owner can no longer use the resource. I think that's what they're trying to say. This avoids creating dangling pointers. Exactly. Okay. But okay. Ownership and moves. Okay, so that's what it says. And then there's partial moves. Move by whatever. Borrowing. Most of the time we'd like to access data without taking ownership. To accomplish this, Rust uses a borrowing mechanism. Instead of passing objects by value, okay. So I guess what it's telling me is that we should be using, we're not gonna skip all the way down to 15. So move is kind of a dead end, and I guess we can use move to move it back. Although I'm not sure how we do that. Or maybe, yeah. Well, maybe we can put a move in here to move it back. But how? Somehow. That seems weird. I don't know how you'd reference the parent. Anyway. But it would appear that move is kind of more severe and final. And generally speaking, we want to borrow, which is what we were doing up here with this reference. Okay, so let's move on. All right. As input parameters. That's a beautiful title. Okay. So closures as input parameters. While Rust chooses how to capture variables on the fly, mostly without type annotation, this ambiguity is not allowed when writing functions. When taking a closure as an input parameter, the closure's complete type must be annotated. They're determined by what the closure does with the captured value. In order of decreasing restriction, they are fun, funmut, funonce. The closure uses the captured value by reference. The closure uses the captured value by mutable reference. The closure uses the captured value by t. Okay. Capture variables in the least restrictive manner. I think we played around with this also. Yeah, we did. With the fun mutt. We played around with this. Okay. I'm not going to go back and talk about it again. All right. Type anonymity. I think this is as far as we got. Closures succinctly capture, sure, according to you, variables from enclosed scopes. Does this have any consequence? Sure. It does. Surely it does. Okay. All right. A little dramatic in the writing here. Observe how using a closure as a function parameter requires generics, which is necessary because of how they are defined. Okay. F must be generic. F, where F. Okay. When a closure is defined, so, all right, let me just go and read the definition of generics to make sure what I think and what they think are the same thing. Open link in new tab. Generics. Oh yeah, 14. Of course. Generics is the topic of generalizing types and functionalities to broader cases. Useful for reducing code duplication. Namely, okay, type parameters specified. Generic type parameters are typically represented as T. Okay, that's typically in C# we would do the same thing. We would have angle bracket some data type to specify the data type, and then we use T and U and V and whatever else you want, but typically T to as the first one to specify that this is a generic type that can be replaced by any type that works in the context. In-rise generic also describes anything that accepts one or more generic parameters. Any type specified as a generic parameter type parameter is generic, and everything else is concrete. Okay, that's a circular thing. For example, defining a generic function named foo that takes an argument of type T of any type. So foo T takes an argument of T. Because T has been specified as generic type parameter using T, it is considered generic. This is the case even if T is previously defined as a struct. Okay. Right. Single A. Defining the type single. The first use of A is not preceded by A, therefore single is a concrete type, and A is defined above, struct A. Here T precedes the first use of T, so angle brackets T. So single gen is a generic type because the type parameter T is generic. It should be anything including concrete type A. So you go single gen T. So you specify that, hey, this is a generic type, and then it takes that generic type as a parameter. It could also return that generic type. Like, you know, you could have, or at least, I don't know, in C# you can at least. You can say, yeah, it returns a type of that, and then you can pass some parameters that are concrete types, and then have it return a generic type. A lot of the time, though, it's like, you know, if you have, like, there's, if you have, let's say you want to do a sort, and sometimes you want to sort on strings, sometimes you want to sort on objects, sometimes you want to sort on whatever, you know, some element of an object, whatever. So you can say sort angle brackets T, and then say, okay, I'm going to specify what we're going to be sorting on here. Another place it's used a lot is in link, where you have the link syntax, although generally speaking it again, probably just like this is about to tell me, C# will figure that out for you. So generally speaking, you don't have to specify the angle brackets to specify the type, because it's figured out from the context. And I'm guessing that that's what's going to happen here. Anyway, okay, so we're on the same page. So yeah, so in this case, they used F, where typically, again, T is kind of the standard thing, the letter that is everybody uses to indicate, yeah, we're creating a generic function. But here we used F. And I guess it doesn't matter what letter you use, as long as you put it in the angle brackets first, it's going to interpret that as a generic. The compiler implicitly creates a new anonymous structure to store the captured variables inside, meaning implementing the function. Okay. Since this new type is of unknown type, any usage in a function will require generics. However, an unbound type parameter T would still be ambiguous and not be allowed, thus bounding by one of the traits. Once, which it implements, is sufficient to specify its type. So So we're going to implement f must implement fun for a closure which takes no inputs and returns nothing. Okay. Apply print. So we're going to pass in print, and print is, oh, I see why they used an f, because they wanted to indicate that the generic is some generic function. So capture x into anonymous type and manipulate fn for it, store it in print. Okay. All right. Sure. This is just weird. Well, you know what? We'll bump into this later, hopefully, and at that time, we'll figure it out. But I guess it's nice to know that we need to do this. Although I'm sure the compiler is going to tell us when we go to create something where we pass in a function and it says, no, you have to have a generic, and then we'll go, oh right, we have to do that, and then we're all set. Input functions. Since closures may be used as arguments, you might wonder if the same can be said about functions, and indeed they can. Again, yes, a little drama. If you declare a function that takes a closure as a parameter, then any function that satisfies the trait bound of that closure can be passed as a parameter. So call me fun. Oh, that's different. Oh, that's the closing arrow. So that's kind of funky. Okay, this is different because typically you in C#, I don't think you'd be able to write that. I think you're stuck with like T or F, but this, we've got an F, and we've said, oh, because that's just data type. But if that's, all right, if that's the data type, then why not just make this a concrete function? Because it's a closure, and a closure, call me this. Yeah, because, oh no, but call me is not a closure. It's calling a closure, but I don't know. I'm not sure what it's trying to tell me here. This seems a little weird. But okay, we'll take it as on face value. As output parameters. Closures as input parameters are possible, so returning closures as output parameters should also be possible. However, anonymous closure types are by definition unknown, so we have to use implement trait to return them. The valid traits for returning a closure are fun, once. Beyond this, the move keyword must be used, which signals that all captures occur by value. This is required because any captures by reference will be dropped as soon as the function is exited, leaving invalid references in the closure. Okay, I'll take your word for it. So we have to use move. So we have a create, which would implement the return. So that's the return value. Let text fin to owned. Print, this is a fin to owned. To owned. Move. Oh. I needed to I think this, what does this do? This must convert this string into a owned. So I own it because I'm going to be passing it into the move or to this, right? And I need to own it. So then I'm going to create a function, create fn mut, okay, and then function plain, function mut, function once. Okay, this. All right, I think it's time to write some code here. Let's play around with this. I'm not sure what this to own thing is doing. So let's find out. All right. And here we go. Okay. So let's close this. Close folder. Start up a terminal. Change directory c:/rust cargo new. Sorry. What shall I call this? This is output closure. It's a long-winded name, but output closure. Okay, and now file, open folder, output closure. Oops, I didn't mean to do that. I meant to do that. Okay, here we go. Main, Control A to select all, Control V to paste. Okay. And already it's complaining because, right? All right, let's rename this. Quick fix. No, I don't want it. Oh, it's spelling mistake. Okay. Yeah, C spell is complaining. Okay, so let me just do this. Funmut. And then I'm going to funmut. And fun once. And I go to fun once. Okay. Now nobody's complaining because it's using the underscore snake case and whatever. Okay, so let's run this and see what happens. Okay, this is a fun mutt, this is a fun once. So this is fun to owned. Okay, so now if I don't do this, if I remove this semicolon / save that, and let me run it. Okay, no difference. So why did we do this? What was the point of this? Creates own data from borrowed data, usually by cloning. Oh, okay, so so maybe in this particular case it doesn't matter whether we own it or not because we're only printing it. But in other situations we might care, maybe, but I don't know. Don't really understand. Create own data from borrowed data, usually by cloning. Okay. Oh, okay. So if I own it, then I can do whatever I want with it, right? I suppose. All right. Well, I guess I don't know what else I can do here. Fun plane. Create fun. Okay. Create fun. Yeah. All right. Well, that kind of was a dead end. I don't know. I'm not sure why they did the to own thing, other than to confuse everybody, because we didn't seem to need it. Now, do we need? Did we need the move? What if we got rid of the move? And let's run this again. Oh, no. Now we got an error. Okay, here we go. Expected a fun closure found just empty. Oh, implement fun. So the implementation of fun. Okay. Well, yeah, I don't know. I don't see in these examples, I don't see using a fun parameter. Oh, but this is not a fun return value. They don't give an example with a fun return value. All right, all right, all right, all right. So the move is required, but the toOwned was not. Okay, gotcha. Okay, I guess we're moving on. I'm not sure that there's any more I can learn from that. This section contains a few examples of using closures from the standard library. Okay. Iterator any is a function which, when passed an iterator, will return true if any element satisfies the predicate, otherwise false. So iterator any bool where f self item bool. Say what? But I thought this was an example. Iterator any pub trait iterator. Oh, okay. So I got it. Okay. So there's a trait called iterator. It has a function called any. So this, by the way, is link. Link in C# has an any, which does the same behavior. Except we don't have to implement it because it's done with generics. Haha. And you pass in a predicate and it goes and does its thing. Now let's see what we have to do here. Like, what extra do we have to do here to make this work in Rust? Okay, so first of all, we had to create this pub trait iterator. And any takes mutable self, meaning the color may be borrowed and modified but not consumed. Okay, fair enough. Well, we don't actually, we want to borrow it. We don't want to modify it, generally speaking. Okay. So, and we're going to pass in a generic function of type F, right? So this is our type F. We're passing in. Now, this is interesting. This is interesting. Fmut meaning any captured variable may at most be modified, not consumed. Self item states it takes arguments to the closure by value. So this is saying by value, and it returns a Boolean. Oh, hang on. Where anywhere fmut. Oh, there's a where clause here to specify some more information about f. Holy cow. So, okay. So we're saying, hey, the anything takes a generic f, and we're going to pass ourselves and this generic f, and it's going to return a Boolean. But further, we want to specify that f is a funmut that takes an item from self, and it returns a Boolean. So that kind of makes sense, right? Because if we're going to do an any, what we're going to do is we're going to loop over each item and ask the question, hey, does this item meet the requirement? And if it does, it's going to return true. If it doesn't, it's going to return false. And presumably, any has some logic in it. Says as soon as the first one returns true, then I can stop looping and return true because I found one. And so any would be just find the first one. And if you found, so the worst case would be not finding any because you'd have to look at all of them to find that you didn't find it. All right. So let's look at its in use. So here I'm saying any, and I'm passing in this closure where I'm taking X and I am comparing X to 2. So I'm saying, hey, are any of these vec1 iterator, are any of them equal to 2? And then here, vec2 into iterator. Okay, iterator for vec yields ampersand I32, destructured to I32. Into iter yields I32, no destructuring required. How the heck was I supposed to know that? All right, let me copy this. All right, let me copy this. What the heck is going on here? All right, we're going to, because this was boring, so I'm not even going to bother with this. Select all. I'm just going to do this, and I'm going to take this one, copy that, and we're going to paste it up here. Oh, just one line, it's fine. Okay, what's this? What? Oh, okay, it's fine. It's just, I didn't save it, and it was giving me an error from before. That was interesting. Okay, so we have this iterator, self, item, bool. This, now we're getting into some weird syntax, because I have not seen this where before to specify more detail about f. So that's something new. And type item. Okay. And what's item? What's the type being iterated over? Item. I don't understand. Because here, I don't see item anywhere. So, all right, I don't get it. But this looks like a keyword. Pub type item. Yeah, I don't understand. I guess maybe it's part of iterator, but it just seems weird that this item thing just kind of shows up out of the blue. Okay. Well, let's just run this once just to make sure that it works. 2 in vec true, 2 in vec 2 false, vec1 length is 3, first element of vec is 1, 2 in array 1 true, 2 in array 2 false. Right, okay. So, yeah, and that makes sense because 2 is here, but it's not there in 4, 5, 6. Okay, and the length, iter only borrows vec in its elements, so they can be used again. Okay, so there's our length. So when we did the move, remember last time we did the move, we couldn't do that. So here, because we're borrowing and not moving, then we can still access vec once we're done, and we can still go get its first element. Okay, and then here array 1, array 2. Right, iter into iter. Now here's the interesting bit. Here is into iter does move vec2 and its elements, so they cannot be used again. So let's uncomment these lines. Save that. Oh, and there we go. Complain. Borrow of moved value vec2. Value borrowed here after move. Vec2 move due to this method call. Move occurs because vec2 has type vec I32, which does not implement the copy trait. Oh, we've seen that message before. This function takes ownership of the receiver self, which moves vec32. Okay, so we're getting a whole bunch of information here, but basically what it means is no, you can't. So the advantage of into iter was that we didn't need to destructure, but the disadvantage is that in order to not destructure, or not to have to destructure here, it had to move. So it creates a consuming iterator, that is one that moves each value out of the vector. Vector cannot be used after calling this. Oh, and we ran into this before, right? Where I tried to reuse the vector and even repopulate it, and it wouldn't work. I actually had to create a brand new vector into the same variable, but a brand new vector, and then I could start accessing it again. So this consuming thing it's gone. Now that actually is, I guess, is kind of handy in some circumstances. You know, I mean, if I'm looking through a list of things and I'm looking for something and the rest I don't care about, and I will never care about them, then I could see that. Typically though, I guess if I'm receiving, I don't know, if you're doing an embedded system and I receive a block of data and I want to parse through the block of data and I want to find some particular value, so I'm going to look at the bytes and I'm going to read the bytes, and as I read the bytes, they are going to be released, and then once I'm done, I don't have to worry about it because that block of memory has been released. So that's kind of cool, I guess, because I don't have to do okay, I'm releasing this now, but did I really have to do that? It didn't seem like I had to do that because all this stuff is on the stack. So as soon as I return, it's gone. Oh, which actually is interesting about the closures, right? Because you're calling a function, but it's able to reach into the stack variables of the caller. That's kind of cool. Okay, so yeah, maybe, sorta, kinda, I could see some uses for it, but I think in my general code, most of the time, I have a list of things or something I want to look through, but I usually want to look through it multiple times. Like a list of products or a list of invoices or whatever, and I want to keep, like, I don't want to throw all this stuff away because then I have to go get it again. So it's like read from a database, and then as I'm going to loop through all user records and read them, but if I consume them as I'm reading them, then and to look for the user I care about, then I have to go back to the database and go get all the users one more time and to go get the next user. So typically, right, you'd read it, you'd cache it, and so that would be where the borrow comes in. And so that means that and so this is dangerous here, right? Because so you got to look for this consuming iterator, because this one returns an iterator. So that's a key thing here. I wonder, is there any way to get out early? Will this return early? Any is short-circuiting, yeah. In other words, it will stop processing as soon as it finds a true. Perfect. Okay. Yeah, that's good. Okay. So I wonder how you do that. I wonder how you write short-circuiting code. Because it's not up here. This is just a definition of what this data type should be, right? Because that ampersand x is, What is it? So we're passing in an f, and the f is a fun mutt. So that's a fun mutt. But we're not actually mutating x, but I guess because we needed to pass the... Okay. So if I just said fun, what would happen here? No complaints so far. Oh, it works. So, yeah, I could use fun here. Fun mutt meaning any captured variable may at most be modified, not consumed. Self item states it takes arguments to closure by value. But it could be just fun because any is only reading, right? So we don't need to mutate things. We don't actually need to borrow things. We're just doing a comparison. Although I guess you could do something more complicated in here. You could modify it. Let's see. If I said x divided by 3, x divided by 3. So if I'm modifying it, is that going to make a difference? No, that doesn't make a difference. So what if I did curly brackets? And then we'll do x equals 3 times x, and then okay. Oh, here we go. That complained. Cannot assign twice to a mutable variable x. Right, because it's not... but... Okay, yeah. Yeah, but what if we did a fun mutt here? Are you happy now? No, you're still not happy. Oh, but I think I need to do a mutt. Oh, what's wrong now? Mutable variable mutt can be used in several situations. What's the error, though? Here we go. Add mutt to each binding. Mutt must be attached to each individual binding. Mutt must be followed by variable and variable add pattern. Huh. What does that mean exactly? Oh, is it? Oh, I think it's ampersand mutt x, not x or mutt ampersand x. All right, that's still an error. What now? Expected reference ampersand integer found mutable reference. Okay. No, it's not. Telling it that it's an I32 is still not satisfying it. Mismatch types. Expected I32 found mutable reference underscore. Expect due to this. To declare a mutable parameter, use to take a parameter x by reference, move mutt to the type. All right. Where's my type? Oh well. Unless what it's actually complaining about is the fact that this is not mutable. Is it mutt let or let mutt? No, it's not that. What now? Let mutt, yeah. Yeah, I'm doing the syntax right. So, let's find it. Oh, but I think it's a yellow underline, so it's not an error. It's quick fix. Remove this mutt. Variable does not need to be mutable. Oh, okay. Well, but I wanted to. Here. I wanted to. How about. Oops. Control Z. Delete. No. What's it complaining about now? Oh dear. Okay. We're still getting this weird, unclear what the problem is. All right. I give up. I don't know what the problem is here. All right, but I know I can't do this. But I could do that because that's okay. All right, everybody's happy. We're back to being happy. Although I don't need the curly brackets. Okay. So run. Do you notice, by the way, that this second one is now returning true? It says 2 in vec2 is true. Well, actually, no, we're not looking for 2. We're looking for something divided by 3 equals 2, which is 6 divided by 3 is 2. So this is actually 6 in vec2 is true. Yeah. Okay. So yeah, I still don't know how to negotiate my way around this mutt business. I wonder if this had something to do with it. But self is already mutable. Don't know. All right. Anyway, I think we're okay. Because that was kind of an artificial example anyway. All right. Where are we at? Okay. Let's save this. Yeah, it's telling me less and less. All right. But that's cool that we have any. So basically, I think looks like we have to do this. And there's a new keyword, by the way, pub, which is what? Who knows? But this boilerplate here seems a little weird to me because, of course, any would take a function, a closure of some kind, and that returns a Boolean, and itself return a Boolean. That's what it does. That's what any does. Always. So why do we have to type all this stuff out? I don't really get. And then where does item come from, and why do we even need to specify type item? Is there other types that we could be doing? All right, back to here again. Are there other types besides item? Type X. How about I32? Oh, I forgot. That's right. This is doing, well, that's weird. Because this does this does that aliasing thing, right? But all right, what the heck? So this is supposed to do an aliasing thing, but it didn't really, because the aliasing thing, where'd that go? Yeah. Type. The aliasing thing has an equal sign. So it's like that equals that. So what does an alias... Oh, here. In traits, type is used to declare an associated type. Okay. All right, off we open. What's an associated? Oh my goodness. Associated types are. All right, here we go. Associated types are type aliases associated with another type. Yeah. But there's no equal sign here. Yeah. What's this? Associated types may include generic parameters and where clauses. These are often referred to as generic associated types, or GATs. Okay. If the type thing has an associated type item from a trait with the generics type can be named like thing as trait item where X is some lifetime and scope. In this case, X will be used wherever A appears in associated definition of an impulse. All right. Well, so this thing, still don't know what this is for. It looks like it's just, all right, who the heck knows? Who the heck knows? This, so it looks like this is used and then we can, so it's only used in the one place here, self item. And then somehow that states that the arguments to the closure are taken by value. So how that says by value, damned if I know. And why this type doesn't have an equal sign, I don't know. This is just mystery syntax with no real good explanation. Okay. Right. Well, I hope you explain it better somewhere along the way here, man, because I'm not getting it. Although the comment says the type being iterated over. So does this mean that this is related to the type of vec1? Which is or I32? Is that what item is? Is item I32? But we can't set a breakpoint. It's weird though, right? Because we can't set a breakpoint here. There's no actual code. There's just a definition of what is going to happen. And this code here, can we set a breakpoint in there? I don't think we're actually. All right, let me see if. What if I put this on a separate line? Can I set a breakpoint on this line? Ooh, looks like I can. All right, let's save that. The formatter will not let me do that. Shoot. Okay. But I suppose what I can do is I can create a closure. Let vec compare equals vertical bar vertical bar, ampersand x, vertical bar, x equals 2. Okay, and then let's replace this with vec compare. All right, I think that's the I think that works out to be the same thing. Let's just run it once just to make sure. Yeah, it's behaving the same way. So if I set a breakpoint here now and debug this, run a debug, yes, okay, yes, okay, close this, we're done. Okay, we hit a breakpoint there, and what is x? Local. Oh, no, this is before we get here. Okay. Continue. Oh, well, maybe. Oh, our local variables are nothing. Static is nothing. We're not getting the call stack here. Output closure main. But I can't look at any variables though. That's the problem. I can't actually. So, sometimes with these functions, you can, or closures, you can set a breakpoint in the mechanism and say, okay, let's find out. All right, let's try. Let's stop this. Let's say one more try. If I put curly brackets here, and then take this and put it there. Now, if I set a breakpoint here, semicolon. Okay. Oh, what's the problem here? Vec compare. Oh, return. Oh, semicolon, right? Semicolon. No semicolon. Ah! Got rid of the curly brackets on me. Formatter, you're making my life difficult here. All right, let's put the curly brackets in. Return curly bracket. Okay, there we go. Now I saved. Oh, I need a semicolon. Save. Okay. There we go. So I can set the breakpoint there. Now let's debug this. Okay, now we're on that line. Can we look at x? Still can't look at x. We still have no access to local variables. But if I set a breakpoint here, oh shoot. Continue. Let's turn this breakpoint off because we can't do anything with that. We continue. Now I get these. Now I get the local variables. So inside this closure, that's not so good. So I can't really debug what's going on inside the closure. I don't like that. At least not with this tool. So if I have something more complicated in there, I'm not going to be able to kind of walk through it and make sure it's doing the right thing. Well, that kind of sucks. Okay. All right. Well, one disappointment after another. All right, let's bop over and see what we got left here. Okay, and then the last one, searching through iterators. Iterator find is a function which iterates over an iterator. Iterates over an iterator and searches for the first value which satisfies some condition. If none of the values satisfy, it returns none. Its signature. Okay, so iterator, item, find, and then we've got predicate P. So instead of the previous one, we used F. This one we're using P, but and predicate instead of, whatever we called it before. What did we call it over here? It was just F, right? So here they're just using different words, but it has the same thing. This is an F. This is the capital F, and it's going to return the item where that returns a Boolean. Meaning any captured variable may at most be modified, not consumed. Yeah, we did whatever. Find double ampersand x equals 2. That's interesting. Iter for vex yields ampersand 32 into iter, right? Well, we figured that one out, right? Because the into was returning the I32. Here, iter for vex returns ampersand 32. We want to reference one of its items, so we have to destructure ampersand 32 to, right? Because the other one we were comparing. This one we actually want to return. So we need to actually get to the actual value, which I guess is double ampersand in this case, because the first ampersand would be, I don't know what the first ampersand, now I'm not sure what's going on here. So what is x? X is, see, thinking of it in terms of C, with the ampersands, x would have been the address of, and then ampersand would have said, the location or the pointer of that place, pointer to that place. And so the double ampersand means that x is a pointer to a place. I find that hard to believe. Because it wasn't before. Why would it be this time? But I suppose it's because we want to return, right? Because this thing, in this particular case, hang on a second. Ampersand self item. So last time, this was just self item is what we're expecting. So here we're expecting ampersand self item. So the address of the item. So the address of the item. I think. Yeah, I think that's where we're going with this. So then it can, grab the item itself. Okay. All right, what's this? It gives you the reference to the item. But if you want index to use the item, use iterator position. So position, hang on a second. Position. Well, did you get to use that without this song and dance? Well, now I need to know. Let me copy this. Were we doing that stuff unnecessarily? Okay. Let's put this right here. Okay. Index of first even number, position of, mod 2 equals 0. Okay, let's save that. And let's run this. Run. Oh, could not compile. What's the error? Linking failed with exit code 1104. Fatal error, cannot open file, output closure.exe. Oh, because it's running. I'm still running. It's like I've run multiple copies now. Okay. So that worked. So hang on a second. So position worked, and I was able to reference position, iter position. So do I really need this any up here? If I delete this or comment this out, how do I comment it out again? I forget. Refactor. No. I don't remember. Let's just delete it temporarily. Let's run this. Save it. Run it. Yeah, it still worked. Okay, so what was that all about? What was all this nonsense up here about any? Why was it even here? What? I guess it was to demonstrate. Okay, it was to demonstrate this. The fact that this is what it was, but we don't have to know this. Okay, all right, that makes me feel better. I don't have to know this in order to be able to use any. Okay, cool. So the heck with this. Goes away. Run this again. Okay, and okay, right, and I want to match index of first even number. How does this match syntax work again? I don't remember. So let's go look here and we'll do Rust lang match syntax. Pattern syntax. Match that curly brackets and then arrows. Okay. Oh, where'd it go? There you are. So curly brackets and then sum x, and then it was double arrow, print line, curly brackets, x, comma, none, arrow, print line, not found. Oh, no, semicolon. Oh, what's this? Oh, I need that in quotes. Okay. Let's run it again. 5. There we go. So that works. Whoa, I'm able to write some Rust code. Would you look at that? Okay, so rather than just using the assert equals this being sum 5, I am actually printing out the 5 here. All right, found index. All right, and 0, 1, 2, 3, 4, 5. That makes sense. Okay. found even at index 5. Perfect. 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 And less than 0, and it's going to say none. Even not found. And we can do the same thing here for this one. First negative number. Found negative index, whatever. Negative number not found. Okay, and now if we run it, found even, yeah. Negative number not found, which makes sense since there is no negative number. Okay, so there we go. Cool. So I've written some actual, real, live Rust code that actually works. All right, cool. I like this. So, you know, this is a fairly common thing to have to do, right? Is you have a vector of something, and then you have to go hunting through it to try to find the thing you want. And either you want to return the thing you found, or you want to return the index. Actually, I wonder. So this is position. Right. So it was the find and then the position. Okay. And so then that's the last thing I'm going to say is all of this business here with this bit of stuff there. I guess maybe that's why they separated it. This is copy and this is like run and whatever, because this is just kind of, oh, it's signature. I didn't, okay, that's what I get for not reading. Okay, yeah. So this is not necessary. Although it was interesting that I copied it in and it still worked. And I was able to modify it too, because I changed the signature to fun instead of fun mutt, and it was still happy. So that's weird. Okay, but whatever. I guess I'm overriding. I'm overriding the behavior? No, that doesn't seem reasonable. Find map. Position. Our position. Position from the right, no doubt. Find map. So find map, if I'm going to guess, is going to find it and then map it to some other object before returning it. Yeah, parse. Okay. Yep. That's exactly what it was doing. Okay. So that's closures. So we're going to move on to higher order functions next time. See how it goes. All right. Thanks for hanging around. Bye.